Hello everybody and welcome back to our artificial intelligence course. So far we have learned about different machine learning models for regression and for classification. We looked at different loss functions and at techniques like regularization to control the complexity of our models. And we have learned about different metrics that can be used for evaluating the performance of classifiers and how we can optimize for the best hyperparameters. In this lecture, we will now learn about a very crucial step that's always needed before we do any machine learning, and that's about data preprocessing and data normalization. So in this lecture, we will look at different types of how we can match samples and how we can filter samples, how we can impute missing values, what is data normalization and standardization, and what's encoding of features and feature transformation. So let's start with matching samples. So in reality, in real-world application, the order of the samples in the feature matrix and our label vector might differ. So for example, you get a set of measurements. Let's say in a genetics data set here we have different samples and we have measured different features, which are, for example, the mutations between the different samples. Then this ordering of the samples in the feature matrix might be different than the ordering of the samples where we have our labels, which tell us, for example, how early a plant flowers or if a specific plant has a disease or not. So this ordering here might differ. So what we have to do in reality, we have to match the samples that the ordering of this feature row is at the same position than in the label. So that S10, for example, in this example, is at the first position in the labels as well. Another problem might be that there might be samples, for example, in the feature matrix that are not present in our labels. So maybe we have measured or genotyped a specific sample, but we never measured any phenotype for it. So for example, we never know if the plant flowers early or late. We just know the genotype. Or for example, if you think about a medical setting, when we have a patient and we sequence this patient, then we might know the differences in the genome of this patient, but we don't know which diseases this patient has. So this might be one of the examples where we have to exclude the sample from our feature matrix. However, it could also happen on the other side, that there are some samples in the labels where we have, for example, measured the disease of a patient, but we never genotyped it. So in this case, we have to also filter the samples in the labels and in the features. So how do we do this? Let's start with matching samples. And in this video, we don't have a real hands-on video. I show it in this slides how we can do the things in NumPy, and afterwards you directly jump into the exercises that you can try out these things yourself. So let's look how we can match up samples. So let's say in this easy example, we have array A, which has a different specific ordering of samples. So we have in this array A 3 different samples, S1, S2, and S3. Then we have another array B, which contains the samples S4, S3, S6, and S1. The ordering here is important. So now we would like to find out what is the overlap and what are the indices of the samples. So this we can do with logical operations. So first we transform A here into a column vector. So that's a normal row vector, and adding here an additional axis, which you might know from the first lecture, we can transform it into a row vector. So this looks then the following: S1, S2, and S3. And then we use the double equal sign here, so we make a comparison to the array B, and the array B still is a row vector. So what we are doing here within one line is we check first this sample here, the row S1, and then equals to this. So where is S1 in this array? And then we get here a matrix of truth values. So it's always false when it doesn't match, and here it's true because here we found S1 and S1. And the same we do for all the rows within one expression here, and then we always get a true when the value is in both arrays and then we also know the index, and it's always false when, for example, S2 isn't present in the array B. So we store here, for example, this truth array in an additional variable, and then we could use a function in NumPy that's called empty_where. So this function returns indices wherever this truth table is equals to true. So we have here within the parentheses, we have the truth table from before, and we say, give me all the indices for the rows and the columns where we can find a true value. So what we get back here from this expression is a tuple, and this tuple has two arrays. The first array gives me the indices for our matrix A. So it tells me in this array, index 0 and index 2 is also present in B. And also the ordering is here already given. And here in the second element of the of this return statement, we get array 3, 1, which are the indices of B. This tells me here in B, the index 3 is in A and the index 1 is in A. And because it's here in the first position, it also reorders directly this element. So if I use now this index here, so I can access the first tuple with 0, so I can provide or pass this array as an index array using the squared brackets to my variable A, and then I'm getting back here an array which is S1 and S3, and the same I can do for B, but here I have to change the index to 1, that I access here this array, and then it already gives me also the indices in the correct order. So we can see using this truth table here, or this operation, this equality operations, and the function empty_where, we can find the indices and match up the samples. Another problem in real-world datasets is that in real-world datasets we not only have missing samples, so completely missing samples in the feature space or in the label space, but we also might miss individual features. For example, if we think about genetics, it could be that there is no mutation, or it could be that there was a sequencing error, and because of this we didn't measure the mutation. Or in other data sets, like for example, if we would like to recommend which movies a specific person or a specific sample likes, it might be that we haven't measured specific movies, or that we haven't stored specific information for these people. So what we try to do here is we have to somehow impute these missing values, or we have to filter out samples. So these are two different ways. For example, what we could do here, if we look at this row, in this row we can see that there are only 5 features present for sample 11. However, in total there are much more than these 5 features, and this looks like that we are missing a lot of information for this sample. So it might make sense to exclude this sample from our data set. So we could filter out the sample, as also, for example, here we have to filter it out also then from the labels. That would be one possibility, and the other possibility would be that we impute missing values. This means, or this word imputing means, that we try to infer what would be the value of this feature for this sample based on the information we know from the others. We have to say, in a real-world dataset, usually when you import the data, missing values are either illustrated or indicated by the type none, not available number. So empty none could be one type, or it could be just in the dataset a question mark, or it could be just an empty string that at this position there is nothing measured. So there are different ways how missing values might be indicated. So first, let's look at the example how we can filter out or remove samples from our dataset. Before we looked at how we can match up different samples, now we look at how we can remove specific samples. And this we can do also with NumPy. So again, we have here an array which I call sample IDs to remove, which is just a NumPy array which contains 2 samples which I would like to remove from my full sample IDs list. And then I use here exactly the same statement from before. I create this truth table which tells me which samples are present or not. Then I use np_where to get the indices of this truth table, where the indices are true. And this tells me then all the indices that I would like to remove from my dataset. And then I could use np_delete. I provide the array from which I would like to delete. I provide the indices. In this case, I like to provide the indices of 0 because I would like to remove from the sample ID set and along axis equals to 0. The same I do for x, and then I can delete all the rows from the samples which I do not know, which I do not need. So we now know how we can filter or match up samples and how we can remove samples from our dataset. In the next step, we will look at how we can impute missing data. And there are different ways. First, we will look at a very simple idea how we can impute missing values. So let's look here at this feature vector. So we have one column of our matrix X, and this column, for example, is a categorical or binary feature. In this case, it's a binary feature. We only have 1 or 0, and there are 2 missing values here. For sample 3 and for sample 7, we have a none. So we don't know this value. We haven't measured it, or it was not transmitted via email or whatever. It's just missing. What we could now do is that we impute this missing value by using the most frequent value along this feature column J. So we look at this feature column, then we count how often do the specific categories appear. In this case, the 0 is 4 times in this feature column. The 1 is only 2 times in the feature column. So the most frequent value is 0. So then what we would do here in this binary or categorical imputation, we just set these 2 samples to 0 as well. Important is here that we do this individually for each feature. So we can't use for feature xk the same value that we used for feature xj. So we always have to look at the feature column, infer the most frequent value, and then replace the none values or the missing values with this most frequent one. Another simple imputation strategy for continuous features is not using the most frequent value, but using the mean or the median. For example, here we have some continuous levels. Again, here sample 3 and sample 7 are missing. And then we could impute these values by computing the mean along this column and then replacing the none values by the mean or the median, which we have done here. That's very easy, and that we can do because by adding the mean or the most frequent value, we won't really change anything in the data. We just assume they behave like all the others, or like the majority of people in this data set, or that the mean value themselves behave on average like the others. So that's why we can use this imputation strategy. And this can be also done in Python using scikit-learn. So for example, here we have a data matrix X. We have here 3 samples and 3 features, and there are a few none values in the data set. Then we could use the class simple imputer from the sklearn package. And then we have to can initialize this object here. So for example, my object imputer or my variable imputer is equals to simple imputer. Then I provide the missing values. So in our case, missing values are indicated by np.none in our data set, because there are none here. And our strategy is to use the mean imputation. And what we then do is then use this imputer object to fit transform. So fit transform is a method that first fits the data here. So it's computing for each column the mean, and then it's in one step also replacing it And then we have here our x underscore m, our imputed matrix, which looks as following in this case. So here we had 1 and 0, so the mean is 0.5. Here we had 5 and 6, so the mean is 5.5. And here we had 3 and 2, so the mean is 2.5. And then we could replace here these different values. The same, of course, we can do by using the most frequent strategy. So we just change here the strategy to most frequent, and then you see that the result differs. Then we have here a 0 instead of 0.1. Here we have 5, and here we have 2. So using sklearn and the simple imputer clause, we can simply impute our data and replace missing values by either the mean or most frequent value. What's important here to mention is that when we use this imputation, or when we do imputation, we always do it on the training data. And then we know, for example, what was the mean for this feature on the training data, or what was the most frequent value on the training data. And then we use the same data, or the same information for imputing missing values in the test data. We don't do it on the full data set. We do it only in the training data set, and then we apply it to the test data set. And we don't, or redo it on the test data set, because if we recompute, for example, the most frequent value on the test data and replace it, then we might get a different imputation than as we have done it on the training data. So this is important. We do it on the training data, then we apply the values that we have learned to the test data. There is also a more advanced imputation strategy, and that's using k-nearest neighbor. So the idea is that we approximate our missing values by looking at its closest neighbor or neighbors. So that's a very interesting strategy, and that uses the information, or this classification algorithm from before, in a different manner. So here we just say, okay, when we know, or when we can find the closest neighbors to my actual sample, then I know, okay, if this sample is very close, then this feature which is missing might be also very close to the one for which I know the feature. So this is also implemented in sklearn, which is called KNN imputer, and then we can use this KNN imputer to also fit transform here our matrix X, and then we get our imputed matrix. And let's look at some examples, what differences these different imputation strategies do. So if you would like to, before we do this, if you'd like to learn more about these different strategies, I also uploaded additional reading material. These are 2 papers about k-nearest neighbor imputation and a comparison of k-nearest neighbor imputation. And this gives you already an idea how scientific papers look like and how these scientific papers are written, for example, when they deal with machine learning data or machine learning algorithms. So let's look at an example. Let's say we have here a matrix with some y values and some x values, and actually this was an image. I just randomly deleted 75% of all the pixels. So through random sampling, I just deleted randomly 75% of the data. And this you can see here, this image just looks like a few dots. It's really difficult to infer what the real image was. So now let's first take mean imputation. We just take every column here, look at the mean in the column, and then replace all the missing values by the mean. So if we do this, we get the following image. So here you already see, it looks a little bit better, and now we can see some structure already in the data. So it's starting to look a little bit more than the image than this, but it's still not very good. But it's better than nothing. So we then can use it in a machine learning algorithm because we don't have any missing data anymore. If we now use k-nearest neighbor imputation with just, for example, one neighbor, we just look at the closest neighbor and infer the pixel, then you see the following image. So here we can see a clear image now. So one of the images which we used in our first exercise. And you can see that based on, or using this image where we can't really see anything and where only 25% of the data is present, and all the rest was missing, using k-nearest neighbor imputation, we already could restore more or less the original image from before. And that's quite amazing. And for example, if we use other random noise ratios, for example with 20%, then we still can see here the image, but all these white dots indicate that there is something missing. And missing data can't be, or data matrices where we don't have any entry can't be used in a machine learning model. So we somehow have to impute or infer the data. And when we then use mean imputation, then you see, okay, this image now looks much, much better than this one. So we could use the mean imputation, the simple imputation already, when we only have a few data points missing. So 20% is already quite a lot. But this, when then using mean imputation, this already helps that we get a better data set that can be used. And here KNN already leads more or less almost to the original image, which you can see here, which you could see here. Here we have 40% noise. Here also mean imputation still works quite well compared to the KNN imputation. Of course, it loses. And here again, you see the original image, and below it was the 75%. So you can see with k-nearest neighbor imputation, it already gives you very, very good results, even if you have a lot of data missing randomly. The next thing which I will talk about is, what do we do if we have categorical features? We always talk now about continuous features or binary features, but very often we have categorical features. And there we have to distinguish between two features, or between two different categorical data types. One is ordinal data and the other one is nominal data. So ordinal data is categorical data that can be sorted or ordered. That's, for example, grades, like good, bad. This can be ordered in a specific manner. T-shirt sizes, like small, medium, large. This has an order, so we can use this order to encode our data. Or nominal data, in contrast to ordinal data, is that we can't imply any orders based on the values we are provided. And this is, for example, color. It could be that we have a feature vector, and in one column we only get strings which tell me green, red, blue, or whatever. So these are different categories, and we just can't assign them any numbers because there is no order for it. Or a car model, or the style of a haircut. This might be categories, but there is no order. So how, or what do we do if we have ordinal data? So ordinal data, we have to encode into integers. And these integers then can be used in our machine learning model again. So for example, let's say we have here a feature column, and this feature column has the sizes of a shirt, L, XL, M, S, and so on. Because we always use mathematical models here, mathematical models can't use the letter L. It doesn't mean anything to our machine learning model. So we have to encode these strings into some numbers. And this we can do in the following. So first, we get the unique elements in this list here, which is in our case L, XL, M, and S. And we know that there is an order in our case. So there is a meaningful encoding and a bad encoding. And a meaningful encoding would be that S gets the smallest value because it's the smallest size that we have in our data set here. M gets the next biggest integer, L the next biggest, and XL the highest integer. And so these integers now increase with the size of the shirt. So this is meaningful because here a 4 is in a mathematical sense higher than a 1. And also the shirt size XL is larger than this shirt size S. So this ordering and this encoding makes a lot of sense, also from a mathematical perspective. A bad encoding would be, for example, if we say S is 4 and L is 1 and so on, because there we don't know what these integers mean. So Y, for example, has a shirt of size S a higher value than a shirt of size L. And this also would indicate here that, for example, a shirt of size S would weigh 4 times higher than a shirt of size L. So this encoding doesn't make any sense and would mislead our machine learning model, and we can't learn anything, or we might learn spurious or bad connections or wrong connections that are not useful at all. So ordinal data we now know how to encode, but what's about nominal data? As we said, nominal data has no particular order. So to encode such data, what we have to do is we have to create so-called dummy variables. And that we can do this, we can use a technique that's called one-hot encoding. So what we do in one-hot encoding is that we convert a single feature into several binary features. So let's look at an example. Let's say we have here a feature column, and in the feature column we have stored different colors like blue, green, red, and so on. So what we do here is that we create for each category a new vector, a new dummy variable, which is either 0 or 1. So we create a binary feature variable for red, for green, and for blue. So this single one is now transformed into 3 features, which then tells me, is it red? No. Is it green? No. Is it blue? Yes. And this we do for all the features here, for all the rows. And then we have one-hot encoded here, this nominal data. And here, this is just a truth value, yes or no. And this can be then used as features in our machine learning model. So this could be also when we have more categories, like let's say 10 categories, then we will get 10 different feature encodings here, one-hot encodings. And this, of course, can be also done in scikit-learn. Let's say we have here this data matrix X, where we have here 2 normal features, which are integers, for example, and here we have this nominal feature column, which tells me that's green, here it's red, this sample is green. Then we could import from sklearn the one-hot encoder from the preprocessing package. We initialize it here with encoders equals to one-hot encoder, and then we can write our transformed feature xe is encoder.fit transform, and then we pass here just the indices of the features which I would like to encode or one-hot encode, and that's only here starting at index 2 until the end, and then we will get back here 2 features because we have here green and red. It's then green and that's red, which tells me this sample is green, but it's not red. This sample is not green, but it's red, and so on. So with this, we then can encode our data as well. And the last thing which I would like to talk about in this lecture is feature standardization and normalization. So feature scaling, that's nothing else than standardization or normalization of our features, is one of the most crucial steps before we run any machine learning model. The problem is that most of our machine learning models are not scale invariant. What does this mean? Feature scaling leads, well, let's go one step back. So feature scaling is important because it leads to more stable parameters and it might faster converge. So when we have an optimization algorithm like gradient descent, or when we optimize the L2 loss, it might converge faster. And so why is this important now? Let's look at an example here. So let's assume we are given 2 features. The first feature has a range, for example, between the value 1 and the value 20. And the second feature has a range starting at 100 up to 20,000. So 2 different features, 2 different scales. So let's assume now we compute the L2 loss, so the squared error. When we compute here the squared error, the error might be much, much smaller than if we would compute it here. So if we compute here an error, let's say between 200 and 150, we get a much larger error if we compute an error here between 1 and 5. So the problem is then, this squared error is then dominated by the second feature, by this feature here, which it has this larger range compared to this feature. And this might be a problem, because then our optimization problem is more or less only dominated by this feature. The same is true if we look, for example, at a different model when we say use the Euclidean distance in a k-nearest neighbor classifier. If we would like to compute the distance between samples, then the Euclidean distance is also dominated by this feature, because this then leads to a much larger distance. And the problem is, if we have these large values in our data set, then distances between the samples might get arbitrarily large. So that's why we have to somehow account for this different scaling of our features. And there are different techniques that can be used. One technique is the so-called min-max scaling. Min-max scaling rescales each individual feature j to a range between 0 and 1. So what we do here is we take our feature, for example feature 1, and we scale the numbers here, the 1 to 20, between the range of 0 and 1. And the same we do for the second feature. We transform it into a range between 0 and 1. And this can be done as follows. So our xj for sample I is nothing else than this data point minus the minimum of the feature column j divided by the maximum value in the feature column j minus the minimum value in the feature column j. And this then transforms all the values between 0 and 1. And this can be done also in scikit-learn. It's called min-max scalar. So we can import the min-max scalar from the preprocessing package. Then we initialize the object here, and then we say, okay, our x training is equals to min-max dot fit transform. So we pass here our x training data, and then it gets transformed into x train. So this is then already between, so here it might be between 1 and 20, and here it's then between 1 and 0. And the important thing is now that we always compute these transformations on our training data set. And when we then test on our test data set, then we apply the values that we have learned. So in this case, the minimum value and the maximum value, we take them from the training set and apply them on the test set. And then we are sure that the values are also between 0 and 1. Another technique is to standardize the features or to center the features around the mean 0, and that we normalize them in such a way that they have a standard deviation of 1. And the nice thing about this is that this does not change the relative differences of our features between the samples. And this is a very important normalization technique that is very useful when we train a logistic regression model or a support vector machine, because first of all, they converge much faster and we get more stable solutions in terms of the weights. What or how can we do this? So what we do here is we subtract from this element here, we subtract the mean of the feature j. So we take the full column, compute the mean, we subtract the mean, and we divide by the standard deviation. And that leads then to a mean that is 0 and to a standard deviation that is 1. And this can be also done in scikit-learn using the standard scalar package. And here we do the same as before. We compute these parameters here on the training data, we transform the training data, and then we apply or we use the same scalar to transform the test data, which is then using the data from or the estimates from our training data. So let's look at an example. Here in blue, you can see a histogram, the original histogram, which is between, so that the mean is around 2.3 approximately here, and it has a quite huge standard deviation. So if we now use this set score, so we compute unit variance and zero mean and unit variance, then we see that the orange histogram here is now centered around 0. So the mean is 0 of this data then, and the standard deviation is 1. So this is normalized. And min-max normalization then always shrinks the data into the range between 0 and 1. And you can see that in general the distribution looks the same, but it is either here between 0 and 1 or centered around 0 and has a standard deviation of 1. So standardization and normalizations are important and have to be done before running any machine learning model, or it's always wise to do it. And these standardizations, they help to mediate the effect of different scales of our features. And it helps to also speed up the training because our algorithms converge much faster. So if you apply some of these techniques to the examples that we have learned in the lectures before, you see that the training is much faster and you don't have to wait so long for the results when you do the exercises, when you transform or when you standardize your data before. However, what's very important, values that we compute, for example, the minimum, the maximum, the mean or standard deviations, have to be always estimated on the training data. And then we have to use the exact same parameters to transform the test data. We are not allowed to compute these values again on the test data set. This would lead then to a wrong normalization. So, what should I know? We should know how we filter or how we match samples. We should know what is imputation and how we can import missing values and why importing missing values is important. And then we have to encode category or text-based features using different techniques like the one-hot encoding, and we have to normalize, or we have to know what is normalization and standardization and why this is important. That brings me to the end of this lecture. As I said, I uploaded some additional reading material for you. That's just optional if you like to see how a paper is written, how, for example, mean imputation or k-nearest neighbor imputation is used in scientific literature. And I uploaded an exercise for you where you can try out all these things and apply it on a toy dataset. So thanks for your attention and see you in our question hour.